My name is Rudy Thiel and welcome to this video explaining my final year project at Stellenbosch University, which is a distributed Minecraft server using Spatial Publish Subscribe. So with the world becoming more connected by the day, more people are playing online games than ever before. One highly popular online gaming category is that of the massively multiplayer online game, or MMOG, which implements a massively multi-user virtual environment, or MMVE. The popularity of these MMVEs, as well as a rising player base, creates the need for them to be able to accommodate a wide range of simultaneous players, i.e. they need to be scalable. Traditional MMVEs typically employ client-server architectures. Each client in the system is directly connected to the server, and all world updates and events are communicated by the server to each client directly. This hinders the scalability of the system due to bandwidth limitations, as well as the fact that the server needs to determine which updates to communicate to which clients, known as interest management. Publish Subscribe is a messaging scheme where the message senders, or publishers, send messages to groups or channels while possessing no knowledge about the message receivers present in the system. Similarly, message receivers have no knowledge about which publishers are present in the system and merely subscribe to various groups or channels to receive messages published to them. Spatial Publish Subscribe, or SPS, extends the concept of Publish Subscribe to spatial dimensions. Each node in a network can specify a publication space as well as a subscription space. Nodes publish messages to their publication space and receive messages from their subscription space. Interest is then determined by a dedicated interest matcher which routes the correct publications to the correct subscribers. Since players are only concerned about what happens in the region around them, called their area of interest, SPS might improve MMVE scalability by removing the interest management from the server and allowing updates and events to be published only once on a per event basis, instead of to each client individually. The main goal of this project was to demonstrate the viability of SPS in improving MMVE scalability by implementing it into the Cookapan project. The objectives of this project included the design and implementation of an application-agnostic interest matcher to handle SPS publications and subscriptions, as well as the necessary proxies to encapsulate Minecraft packets as SPS packets and communicate with the interest matcher. The Cookapan project is a research tool that transforms Minecraft into a platform for MMVE research areas, such as scalability. It employs a distributed server design that partitions the Minecraft world using Voronoi spatial partitioning. Each server node is then assigned as the authority of a certain region and is responsible for handling the event and update dissemination of that region. Clients connect to the server cluster using a client-side proxy, which also handles the migration between servers. The proposed system architecture introduces Spatial Publish Subscribe client and server proxies, as well as an interest matcher into the existing Cookapan architecture. The proxies convert Minecraft packets into SPS packets and publish them to the interest matcher, which keeps a list of subscriptions and determines interest in messages. Firstly, an investigation was done into the spatial nature of Minecraft packets. This was done by modifying the existing client-side proxy in the Cookapan project and keeping track of all packets sent from and to the server in a normal Minecraft session. The following demonstration shows how this was done. Firstly, the proxy is run using the java-jar command, and the server host as well as server port are passed as parameters, as well as the proxy host and proxy port. After the proxy is run, the Minecraft client is opened and a connection is made to the proxy. Upon receipt of a packet, the proxy stores it in a hash map, and each time a new packet of the same type is received, the proxy increments the counter in the hash map, keeping tab of which packets have been sent how many times. The investigation showed that the top 6 client-bound packets accounted for 83% of packets sent by the server, and the top 4 server-bound packets accounted for 87% of packets sent by the client. Furthermore, it was found that 93% of server-bound and 98% of client-bound packets contain spatial information. While the majority of packets were found to originate from specific spatial coordinates, there were packets which contained no spatial information whatsoever. In order for the interest matcher to handle packets with various levels of spatial information, the following scopes were implemented to classify each packet: spatial, server, global, and player. With the packet scopes defined, we now turn to the design of the interest matcher. A main goal of this project was that the interest matcher should be application agnostic. This means that the matcher should be independent of the application in which it is used, in this case Minecraft. While keeping the matcher application agnostic, we define 3 assumptions that applications should adhere to in order to communicate over SPS through the interest matcher. Firstly, we assume that there are 2 types of nodes in the network: server nodes and client nodes. Secondly, we assume that no server-to-server or client-to-client communication happens over the SPS layer. And lastly, we assume that all nodes in the network may only subscribe to one area at a given time. Future work for this project includes integrating the matcher with Vast, a JavaScript SPS library. For this reason, the interest matcher was written in JavaScript. Node.js was used as a framework for running the matcher as a listening server that listens for new publications and subscriptions. Server-sent events and WebSockets were investigated as protocols for communication between the matcher and proxies. WebSockets were chosen because they provide full duplex communication over a persistent connection. The Socket.io library was chosen to handle the communication since it provides a Java implementation and the proxies are Java-based due to the Cookapan architecture. The matcher determines interest in messages using various algorithms designed throughout this project. Some packet scopes require basic algebra to determine interest, while others require the use of the separating axis theorem. World states are managed through the use of 2 layers of SPS, one layer for updates and one layer for events, such as player movement generated by clients. Updates are publications by the server. All server publications are published to the updates layer, and all client publications are published to the events layer. The client and server proxies are responsible for intercepting Minecraft packets and wrapping them as spatial publish subscribe packets and attaching a scope to them. They are written in Java and use the MC Protocol lib library to implement the Minecraft protocol. The client proxy acts as a server to the client, and the server proxy acts as a client to the server. Both proxies listen for publications from the matcher, and upon receipt of publications, convert the SPS packets back into Minecraft packets. In order to attach spatial information to every entity packet, the server proxy also keeps track of all entities present on the server through a hash map of entity IDs to entity objects. The following demonstration shows a single client moving through the world in a normal Minecraft setting, followed by a SPS connected client with a very small area of interest moving through the same Minecraft world. When connected over a normal Minecraft connection, the player receives entity updates from all entities within loaded chunks. Whereas when connected over the SPS implementation, the client only receives entity updates from within their area of interest, as seen here by the slime moving. With the matcher and proxies correctly implemented, we turn to the testing of the software, as well as their results. The objectives of this project were evaluated through various metrics, including network throughput, latency, as well as matcher resource consumption. Testing was performed using 2 Raspberry Pis to host 2 servers and a laptop computer to host 2 clients, as well as the client and server proxies. The throughput test showed a 30.59% reduction in network throughput in a system containing 2 clients when using the SPS architecture compared to the existing Cookapan architecture. The latency test showed a discrepancy in the latency introduced by how the matcher handles different packet scopes. It also indicated a maximum of 75 subscriptions in the network before network latency passed a 100 millisecond threshold. Lastly, the resource consumption test indicated that the matcher is lightweight and can easily accommodate in excess of 75 subscriptions while only consuming 80 megabytes of RAM. In conclusion, the main objective of implementing SPS in the Cookapan project was successfully met. SPS was shown to reduce network throughput significantly, and the matcher was demonstrated to be very lightweight. The results demonstrated that SPS has the ability to significantly increase MMVE scalability in a future implementation. This concludes my video presentation. Thank you very much for watching.